Hello, welcome back to my channel. So I'm going to do a video today on the difficulty, the target, and the bits in Bitcoin. And these terms get sort of used sometimes interchangeably, and there's a lot of confusion about what they actually mean. And it's actually quite difficult to find some definitive documentation that tells you exactly what they all are and how they relate to each other. They relate to each other very closely, and this video is going to be all about breaking down that relationship once and for all in quite a low level of detail. So it's going to be quite a technical video. By the way, this is a topic that's kind of not essential to understand the Bitcoin protocol or indeed more importantly the blockchain concept. But for those of you who are sort of more detail oriented and want to kind of get a better understanding of how the difficulty for each block is actually calculated and how it evolves over time, then stay tuned and hopefully I will explain it for you. So in the world of Bitcoin, you'll often hear the target talked about very often, and you'll hear a metric called difficulty. And you'll hear about bits, or you'll see, actually more often you'll see bits as a variable that is that's reported in each block, right? It's part of the block, and bits is an attribute of a block. So these three are closely related, and I think of it often like a triangle. It's like in photography. So it's similar kind of thing here, and I want to sort of break down this whole thing further. Now, so when it comes to target, so a lot of the time, a lot of documentation that you read about in Bitcoin, including my first video introducing this topic, was kind of suggesting that the target for a Bitcoin miner is to produce a hash, right, which has a certain number of leading zeros, right? And the example I gave was a particular block in which the target, or the hash, the actual hash of that block had 17 leading zeros. Okay, I'm not going to draw that out, but basically it's 17 times 0, and then plus, and then some 5 C 2 E F some hash of that block that satisfied a requirement that there had to be 17 leading zeros. Now I'm going to come clean here and say that the target hash for miners, that all you have to do is to hash the block, keep tweaking that nonce and those variable data points that allow you to change the inputs. Keep doing that until you get a hash with, let's say, 17 leading zeros or 18 leading zeros, or however many leading zeros the Bitcoin network is currently saying is the required difficulty. It's not quite as simple as that, and I'm not quite sure why it's. I guess it's probably simplified just because to illustrate the concept, it's kind of neater to say find a hash that that just happens to have a certain number of leading zeros. But in a nutshell, right, what the target really is in terms of Bitcoin mining is quite simple, right? And it's basically, the target is a 256-bit number, right? So 256-bit binary number. Now, binary numbers, as we all know, are represented as normally represented as zeros and ones. They don't have to be zeros and ones, but the whole point of binary is that it's basically a two-state numerical system, and so we represent a 256-bit number as something like 0001001001 all the way up to 256. So 256 of those digits, right? And that gives you your binary number. Now, so what we're saying is that as we all know, hopefully by now, if you haven't seen the previous videos on hashing, then please have a look at them. So the block header is going through a 256 bit hashing algorithm, right? So the output is going to be 256 bits, and the target. So instead of saying the target has to start with a 17 leading zeros in hexadecimal, the reality is the target is such that the hash of the block has to be less than the target binary number, less than or equal. My apologies, right? So often the two are correlated, as in obviously a number in binary that has more leading zeros is obviously a lower number. So if you find a hash that has more leading zeros than the target, then obviously your hash will be successful. But it's quite possible that you will find this is the particular kind of corner case. It's perfectly possible that you'll find a hash which has the same leading zeros as the target. So in this case, if the target had 17 leading zeros, it's possible that your hash would actually be a greater binary number than the target, right? Even though it has 17 leading zeros. So the key point is that the target is just a 256-bit binary number, okay? And the winning hash is equal to or less than that target, right? So it's not quite as simple as saying there are, it's just so many leading zeros. And if you think about it, right, if it were the case that it was just about the number of leading zeros, so from week to week, or more specifically from 2 weeks to 2 weeks, because as we know that's roughly how often the target difficulty gets adjusted. If that were to happen, that it's only the matter of 17 leading zeros changing to 18 leading zeros, changing to 19, changing to back to 17. If that were the case, then the only flexibility in terms of adjusting the difficulty would be to make it either twice as difficult or half as difficult. Because each time, if you say, okay, that the binary hash has to start with 3 leading zeros 1 week, right? But then the following week it has to start with 4 leading zeros, then you're basically you're making it twice as difficult, right? Because each leading zero decreases your search space by half as much because it's binary, right? So clearly, this is not the level of flexibility that the Bitcoin network wants or needs, right? That they need to be able to say every 2 weeks, right? Every 2 weeks, how long? So I'm going to just write this down. So each 2 weeks, what they say, as in what the Bitcoin nodes who are basically validating and determining what the difficulty on each block should be, they say essentially. So what's the current difficulty, and I'll go into more details about what that actually means, right? Multiplied by the time to generate the last 2016 blocks, right? Divided by 20,160, and this is in minutes, right? So clearly, and this quantity here, this big thing here, this is used to create the next difficulty, right? Or more specifically, the next target, right? So actually, I'm going to scratch that out and say next target, because as you saw, difficulty is actually something quite different. But the target is this number that we're trying to get a hash that's less than that number, right? So basically, what we're saying is that I'm trying to illustrate the point that so clearly, the ratio between the time for the last 2016 blocks and the number of minutes, right? This is the number of minutes in 2 weeks. That ratio is quite a granular ratio, right? And that's the whole point. We want to be able to adjust this difficulty on a more granular level than either doubling it or halving it, right? So all I'm trying to say is, and it's a kind of I guess a long-winded way of saying it, but it's not. I'm just going to write it here. So it's not just leading zeros, right? Or in fact, let's just say it's not about leading zeros, right? So just like internalize that in your head, right? It's not about leading zeros. It's ultimately about target. The target, and this changes roughly every 2 weeks, is a 256-bit number, right? And the winning hash, right? The winning hash, the valid hash block that a miner produces, is basically less than or equal to that number, right? So that's the myth that I'm trying to dispel here, and I'm going to go into more detail now about what's the difference between and what they all are, how you derive them, difficulty, bits, and target. Okay, so we're back on blockchain.info, and I'm going to go into a couple of fields that we haven't actually looked for on the previous videos. And the two fields that I really want to focus on in this video are the difficulty, which in this case is 1. Now this is our good old friend block number 0. So this is our Genesis block, the first block ever in the blockchain. And I want to both these values here are very, very important when you're talking about difficulty. Okay. Now we're going to talk about what difficulty is. We're going to talk about bits is. Now I'm going to take it step by step. The first of these difficulty bits and target things I talked about was the target. So explaining that the hash, which you can see up here, right, which was the successful hash for block number 0, the Genesis block, that has to be less than a specific binary number, right? A 256-bit binary number. This hash has to be less than that for it to be successful. and that number is this one here. Now, that looks confusing. First of all, that's not a binary representation, that's a decimal representation. But this number here, first, and you also think, well, 256-bit number is like a really long, verbose number. This is only a few digits, and obviously it's a different base. This is a base 10 representation, and 256 is a binary number. But this number here tells you everything you need to know about the exact number, the exact target, which defined what the successful hash had to be equal to or less than for this particular block. Okay, so that's a decimal number, and I'm going to show you another blockchain explorer. Because in this particular case, the hexadecimal representation of bits, and I didn't really mention, so bits is in any block, right? If I just pick a random block like 3, 4, 6, 7, 3, 4, 5, 6, 7, bits of that block tells you in a kind of specially encoded way what the hash target was for that block, right? So you can work back from this and derive a big long binary number that tells you what the hash target was, right? I'm going to tell you exactly how that works in a second, right? So let's go back to block number 0, right? And there's another blockchain explorer which is really cool. I really like it. It has some sort of slightly different presentation styles. It's called SmartBit, and I'm going to go there. It has exactly the same information. Don't forget, so blockchain.info and SmartBit and whatever other blockchain explorers there are, they're all just basically front ends that look upon their respective copy of the blockchain, which is duplicated all around the world. So, I just really want to hammer that home. There's no central server that has the blockchain data. So I'm going to go for block 0, right, the Genesis block again. And I'm going to go here. And so here we can see that so the hash for this block ends in E26F. If we go back to blockchain.info, E26F, just to show you that it's the same data set. And on SmartBit is an Australian company, and they're kind of trying to develop a kind of a more, let's say, search-friendly and like the sort of the Google of blockchain, the ability to really sort of do proper, sophisticated searches on the blockchain data. So definitely check that out if you're interested. I'll link it down below. But you can see this is the first ever block, okay, and the difficulty is 1. We'll come to that next. The bits is 1D. 00 FFFF, right? I'm going to write that down in the next on my screen thing in a second. But 1D 00 FFFF is the bits value in hexadecimal for the first ever block, right? And what I want to do is I want to basically break down exactly how to derive the target from this bits value, because target and bits basically are interchangeable, right? So the target is that big long 256-bit binary number, but bits is a compact way of representing that number in hexadecimal. So we know that the bits value, which is a compact representation of what the target was in any block, right? We know that the bits value in the Genesis block, right, was 1D 00 FFFF. So what does that actually mean, right? How do you convert this, right, which is basically a 4-byte number, and this is represented in hex. How do you convert that into a 256-bit or 32-byte hash target, right? Now the first thing you're probably thinking is, well, first of all, I cannot, unless there's some truncation involved, I can't represent a 32-byte number in 4 bytes, and that's absolutely correct. And we'll see in a second that the targets are actually they're truncated to a certain number of significant figures, and that's the way it works. And that's all about again, the truncation is to kind of minimize the amount of space taken up on the blockchain, right, with these hash targets. So basically, the way this works is actually quite straightforward, although at first it can be quite intimidating. It's quite difficult to find any definitive documentation on it. So the way it works is, obviously you need to think about how to expand this number out into binary. But this, I'm just going to take a different color here. These 4 bytes, right? I'm going to take a different color. Oh, there you go. These 4 bytes here, right, which is our bits value in each block, right? We have 1 byte here, and then we have 1, 2, 3. So 4 bytes. Each hexadecimal digit is obviously 4 bits. So 2 hexadecimal digits makes 1 byte. If you're confused about that, leave a comment. If you want a proper dedicated video on hexadecimal notifications, notation, then let me know and I'll do one. So the key point is that the first byte of the bits, right? The first byte is basically the number of bytes that the target number takes up, right? Now the maximum number of bytes that the target can take up is 256. Sorry, is 32, because there are 256 bytes in total. Sorry, 256 bits in total. My apologies. And there are 32 bytes inside the 256 bits, right? 8 bits in a byte. So the first byte tells you basically of if this is the overall space in 256 bits, or 32 bytes, 32 of these, right, in one space. It tells you how many bytes are used to represent the target, and then all the remaining ones are 0, right? So this is a hexadecimal number. It's 1 byte, so it can go anywhere between. So the minimum number for this is 2, and the maximum number is 255. Right, but obviously we know that we can only have a maximum of 32 bytes anyway, because we only have 32 bytes to use here, right? So we don't use all the values in here, but that's fine. Then the remaining three bytes, so 00 in this case 00 FF. Remember, this is the bits value for the first ever Genesis block, right? These define the most significant figures of the target. Right, the most significant figures of the target. Now I'm just going to quickly switch to decimal to give you just a kind of an analogy here, right? So this notation here is known as compact format, right? So it's a compact way of representing a 32 byte number in only 4 bytes, right? So if those of you, some of you might be familiar with floating point, right? Floating point arithmetic. And this is kind of like a floating point notation, right? Now, let me give you an analogy. Let's say that you had, so let's forget about hexadecimal for a second. Let's say we're going back to our good old decimal numbers, just straightforward, 0 to 9, and then 10, 100, 1,000, right? So let's say we have 4 digits of space, right, to represent decimal numbers, and we say. So you want to express a decimal number using 4 digits, right? Now, if you make this one the first digit here, you say, okay, well this one gives me the total number of digits of my number, right? So if and I only have 1 space here, so I can't write 17 here, right? I only have space for 1 digit. So if I write 9 here, right, that means that my overall number is taking up 9 digits, right? And then the remaining 3 digits are used to specify the 3 most significant digits of the number, right? So if I put 4, 2, 5 here, then what this means is that this number here, this way of representing this number, corresponds to 4, 2, 5, which is the 3 most significant digits of our number, and then we know that 9 is the total number of digits, so we basically have 6 remaining to put, right? And so this convention is a way to represent this number, right? So we're saying these significant figures, and then pad it out so that the total number is 9 digits long. I'll give you another example here, just to hammer the point home. So 4 and 137. So 137 is the total number of digits. Sorry, my apologies. 137 is the significant figures. So 137. The total number of digits is 4, so I just pad with 10, right? And this is kind of like a way to represent. So we can. It's kind of like similar to floating point notation, where we say that this is the mantissa, right? So the coefficient. My apologies. The coefficient, and then this is, well, it's not it's kind of the exponent, but we say the convention here would be that. So this is our let's say this is our digit length, right? So we would say our actual number is the coefficient, so 137 times 10 to the power, 10 to the power what, right? So 10 to the power, it's not the digit length, it's the digit length minus the number of digits that we are including as our significant figures, which is 3, right? So digit length minus coefficient digits. Yeah. So digit length in this case is 4. Coefficient digits, so we're using 3 digits here, 3 significant figures, 137, that's 3. So the answer is 137 times 10 to the 1, which is just 11370, right? Which is the number that we originally wanted. So that's an analogy in decimal, and that's exactly how the compact notation works in this compact Bitcoin protocol. The only difference is that the numbers are just a little bit bigger. When I say a little bit bigger, they're a lot bigger, right? So I'm going to try and keep this number in the frame here, and I'm going to say, so in compact notation, instead of having 4 decimal digits, we have 4 bytes, right? 4 bytes. 1, 2, 3, 4, right? Now, the thing about bytes is, so 1 byte equals 8 bits, right? So, for example, 0, 1, 0, 0, 1, 0, 1, 1, right? That's 1 byte, and that's 8 bits, right? Now, that's in binary. Now, so in 1 byte, there are 256 possible values, right? 256. Now, whereas in decimal, right? So in decimal, there are 10 possible values, right? That's what decimal means. There are 10 digits, right? There are basically 0 to 9. In 1 byte, we have 256 possible values, right? So all the different combinations of ones and zeros in 8 zeros and ones, there are 256 possible values. Now, if we think about a hexadecimal notation, why do I say notification? In hexadecimal, what we do is we group 4 bits, right? Each group in a byte, and then we consider the possible values from 0 to 9 and A to F, right? For each of them. So hexadecimal goes from basically, so 1 byte can be 00. That's the minimum value for a byte in hexadecimal, and the maximum value is FF, right? And FF in decimal is 255, and 00 in decimal is obviously just 0. Okay. Now, the leap of faith we've got to make here, it's not really a leap of faith, but it's just like it's slightly different. You know, it makes you really think about numbers. That's why I really love this stuff about the Bitcoin and blockchain stuff. There's so many opportunities to kind of really get back to thinking about what numbers really are, and it kind of gets a bit philosophical at some point, and you kind of think, oh god, this is pretty crazy, but it's kind of fun as well. So if you think that of all the possible hexadecimal values for a byte ranging from 00 to FF, think of each of them as one specific digit, like one specific symbol. Then in actual fact, right, you can actually represent each byte as a sort of a double digit, let's call it double digit hexadecimal number, right? And the key is to think of FF as one symbol, one cohesive symbol representing the decimal number 255, right? So basically, what we're effectively doing is converting, right, to base 256, right? So base 10 is what we're used to, base 2 is binary, base 256 is saying, right, we're now in a counting system where we basically count up from 0 to 255 in one particular column, and then before we carry over, right? So I know I'm going quite a lot of depth here, but and if it's not clear, then please leave questions below, and I will explain them, and I will clarify it, right? So, but the point is that the first bit in this 4-byte bits section, right? This defines how many bytes our target is going to take up. Just like this one here, let me change the color again. In decimal, this value here defines how many digits our overall number that we're trying to represent takes up, right? So and this number here is in hexadecimal, right? So in the case of our Genesis block, right, which if I just scroll up a second, that was 1D, right? The first byte was 1D, right? So our first byte was 1D, and then the second byte was 00, and then the third byte was FF, and the fourth byte was FF. So let's break that down. Well, what does that actually mean? That means that the number that this target represents is, first of all, it takes up 1D bytes, right? So how many bytes is 1D? Well, 1D in hexadecimal is basically 1 times 16 to the power 1 plus D times 16 to the power 0, right? Now D in hexadecimal is, we can go back to our hexadecimal converter, we can see that D corresponds to number 13. So 1D corresponds to 29. So 1D equals, in decimal, equals 16 plus 13 equals 29. So what we're saying is our target takes up 29 out of the 32 bits, right? We know our target, right? Target is 256 bits equals 32 bytes, right? We're saying 29 bytes of this 32 are taken up with these significant bytes, right? Now, once again, the values in here, think of these as individual digits in a base 256 number system, meaning there are 256 possible values for this particular box, right? And FF is one symbol in that box, right? So what we're saying is these 3 bytes are our most significant bytes of a 29 byte number, which has to fit inside our 32 bytes, right? So we have 00 FF, right? So that's a byte, that's a byte, that's a byte, and then we have 26 bytes of 0, right? Because these are the significant bits, as in, so and then everything else is 0. And then on the front we have 32 minus 29 equals 3 bytes of 0, right? So that's what our Genesis block hash looks like. Now that's a lot to get your head around, but it's actually not that complicated when you think about it. What you're basically saying is in base 256, you're saying it's this number here to the power, raised to the power, this number in hex minus 3, and it's exactly the same as what we did. If you're confused about this, just keep going back to this example here, right, where we said we allow 4 digits for our decimal number, right? So we want our decimal number to be 4 digits that we're representing, and the leading digits on the decimal number with everything else 0 are 137. So 137, and then everything else is going to be 0, and then padded out to 4 digits. And it's exactly what we do here, exactly the same thing. You take whatever's in these values here, and then you basically just write them out, and then you say whatever's remaining from 1D is 29 bytes, so remaining 26 bytes we pad out to 0, and then pad the front to 32 bytes because it's 256 bits in total, and that gives you your target, right? So that's how you go from bits to target, right? So far we've seen how to convert from bits to target, right? So bits is what we see in the blockchain, right? We can see on every block we see bits. We know how to convert that bits value to what the actual hash target is in any given block. So for example, so just to recap, in the Genesis block we saw the bits value was in hexadecimal, which is basically this prefix. The value was 1D 00 FF. And to convert that into an actual hash target, we take the last 3 bits, so the last 3 bytes, sorry, of the bits value. So the in this case the 00FF, and then we basically say, well, these are, so we just write these down, 00FF, and then we look at the first byte, sorry, and we see in hexadecimal how many bytes does this represent. In hexadecimal, in this case, it represents 1D is 29, so we know that in total the hash target takes up 29 bits. So 3 from here, and then another 26 bytes of zeros. So 1, 2, all the way to 29, and then the remainder is zeros on the front. In this case, because we have 29 out of 32, we have 3 bytes of zeros, right? And this goes for any bits value in any block that you want to read. That's how you interpret bits and convert it into the actual hash target. If you want to convert this, if you want to sort of expand this into the proper 256-bit hash target, then you expand out these hex values, right? So each of these bytes corresponds to 8 bits, right? And you basically just expand each hexadecimal digit out into its full binary notation, right? So that's hopefully clear on that. So what I want to talk about now is the difficulty aspect. So difficulty really is just a human readable representation of, in relative terms, how difficult that target was to reach from one block to the next, right? And the key thing here is, if we go back to our Genesis block, which was this target here, which was designed by the system to be the first appropriate initialization target, there was a number associated with this target called difficulty, right? And the difficulty of the Genesis block, right, was 1, right? So think of it like, it's like the benchmark. So the first block is defined such that the difficulty is equal to 1, and all subsequent blocks and the difficulty of achieving a hash, right, is all measured against the difficulty of the very first block, right? Now we know that the very first block had a target of this value here, or this value here in hex, right? And that's defined as being a difficulty of 1, right? So difficulty in essence is basically, so if we write it down as, so difficulty D, right? D of any block equals the maximum target divided by the current target, right? So maximum target is this. So don't forget, so the higher this number, the higher this 256-bit number, the easier it is to find a hash that's less than or equal to that number. And that's T max. So T max is T Genesis. And T is the actual current hash target. And the difficulty, D, is the ratio of the two, right? So basically, if at any given time, let's say if we see a block that has difficulty of 2, right, the number 2, what that means is that the T max divided by the current target equals 2, right? Which means that what it effectively means is that the current target is half. Let's write it out. So T current equals T max divided by 2, right? In other words, the target, the actual hash number that we have to produce a block hash that's less than or equal to that number, is half what it was set to right at the beginning in the Genesis block. So I want to kind of go over exactly why. I want to have a look at some of the first few blocks in the blockchain, right, and see how the difficulty evolved over time, right? So if we just jump to our browser, so here we can see there's a website here that shows us the chart of the difficulty over time, right? The difficulty over time, and you can see I can trace down along here and see over time. So starting in January 2009, the difficulty, as I said, started at 1, and if we trace along here, so June, July, August, September, October, the difficulty was still 1, right? In December 2009 and up into January, the difficulty starts increasing to 1.31, 3, 4, and then during 2010 it ramps up quite quickly to 500, 700, 1000, 3000, etc., etc. And then by 2014 it's rapidly increasing, right? So the question is, we know that the difficulty is basically just inversely proportional to the actual hash target. So clearly the hash target is going down over time. So I'll just go back. But what we can see, what we saw is that the difficulty stays at 1 during most of 2009. Now we know that every 2 weeks, the Bitcoin network, every node on the network is recalculating, okay, what is the next appropriate target, the next appropriate hash target to set for the next 2016 blocks, such that we tend towards an average block time of 10 minutes. And so we look at the amount of time that the last 2016 blocks took to complete, and then we compare that with the time period of 2 weeks, and whatever that ratio is, we multiply by the current hash target to get the new hash target. So the question is, why did the difficulty stay at 1 for so long, right? So here we are back at block 1. You can see the difficulty is 1, and as I mentioned, the difficulty is 1 because it's defined as 1 for the first block, right? It's the benchmark. So the first block is defined as having a difficulty of 1. So if we look at the second block, it also has difficulty of 1. That's expected because we expect the difficulty and therefore the hash target to remain the same within a block, within a sequence of 2016 blocks, right? So we expect block 1 and block 1000, right? You can see at block 1000 the difficulty is still 1. We expect that to be the case, but we might expect, if we go to 2000 and say 2018, now we are in the second block, second period of 2016 blocks, and yet the difficulty still stays at 1. Okay, and the reason behind that is, if one of the parameters around the difficulty recalibration is that the difficulty is never allowed to go less than 1, right? So if we actually look at the timestamps, right? So if we look at block number 2015, we see that it actually took 24 days to calculate the first 2016 blocks. Now 24 days later is much more than 2 weeks, right? Much more than 2 weeks. So if we go back to our page, and we say that the target n plus 1 equals the target of n times the time for the last 2016 blocks divided by, this is in minutes, divided by 20,160. That should indicate, so given that this time here is essentially 2 weeks, right? So this number here is more than 2060 because it's more than 2 weeks. So we'd expect the target of block number 2017 or 2016 rather to be larger than the previous target, right? We expect the target to go up, but if the target goes up, that means the difficulty goes down, right? Because if you remember, difficulty equals T max over T, right? So if the target goes up, right? If this goes up, then this is going to go down. But there's a hard limit in the system that says that difficulty is always greater than or equal to 1, right? So there's a hard limit there. So even if we take longer than 2 weeks, and the current difficulty is 1, we don't adjust it. The difficulty stays at 1, right? So that's why we see the difficulty stay the same throughout most of 2009. So during 2009, right, from January all through Feb, March, all the way through to December, it was taking more than 2 weeks to generate 2016 blocks, and that's why the difficulty stayed at 1, because the target was not allowed to go up, even though this formula was dictating that it should, because there was a hard limit, there's a hard ceiling on the target, right? But if we look at a particular block, you can see when the difficulty started to go up, right? So if we see the following, so if we look at block number 30,240. So block 30,240 arrived on the 18th of December 2009 at 9:56 a.m. Right? This is almost 11 months after the first block, and then the next block and the difficulty of this block was still 1. Right? So up to that point, every single block of 2016 blocks had taken more than 2 weeks to generate. But on this occasion, when block number 32,255 came out, on the 30th of December 2009, at 5:58 a.m. Okay, so that block, if you see, for the first time, this particular block, this is 2016 transaction blocks, and they appeared within 12 days of each other, right? So per this formula, this last 2016 blocks was actually, for the first time, was less than 2 weeks, right? In which case, the difficulty for the next 2016 blocks was increased for the first time, right? And we can see this from, if we look at the blockchain website. So if we look at block 32,255, this was the last block where the difficulty was 1. It was issued in 30th of December 2009, has a difficulty of 1, as has all the previous blocks up until this point. But if we look at the next block, 32,256, we see the difficulty goes up to 1.18, right? 1.18. So this is a really good use case just to sort of delve into it a little bit. So 32,256 is is 16 intervals, 16 2-week time intervals into the blockchain, right? So, and on this day, for this block, it said, okay, the block height here is a multiple of 2016, so we're going to recalibrate and see whether we need to update the difficulty. And for the first time, the previous 2016 blocks took less than 2 weeks to calibrate, and therefore we upgraded the difficulty by this much according to the formula, which we have on the screen share. And now the bits of the new block is a new value for the first time. And if we look at this block in our smart bit, so 32,256. If we look at block 32,256, right, and we see that the difficulty again is 1.18. We see here they report the difficulty in bits, right? So it's 1D00 D8 6A. So 1D00 D6, sorry, D8 6A, which is this number here. So if we just to hammer home the point about what we said about how to convert the bits into the target, right? So the target, so we write, so these are the most significant bytes of the target. So we write these down, 00 D8 6A. And this is the number of bytes in total that the target takes up from this point here, which is again 1D, which is 29. So we have, including these ones, 1, 2, 3, and then we have 26 extra bytes of zeros, and then we have 3 extra bytes of zeros on the front. And that's our new target. That's our new actual hash target for the new block, right? So that's really interesting to see. It illustrates that even though the target recalibrates itself every 2 weeks, there is a hard limit, and the difficulty can never go below 1. And it's really important to bear in mind. The difficulty is really just a derived value that's essentially based on the current target and a constant, and the constant is the first ever target in the first Genesis block, right? So going back to where we started from, so we know that bits is the compact representation of the current target, right? So the target is the 256-bit hash number that our block hash has to be equal to or less than. Bits is a compact representation in kind of base 256 floating point format. And difficulty is basically the max target divided by the current target. And the max target is the target from the Genesis block, which is in hexadecimal 1D00FF. So if we actually go back to our blockchain.info site, so if we look at the current block as of the 9th of October 2016, we can see that the difficulty is massively higher than it first was, right? So it's actually it's basically 258 billion times more difficult to generate a successful hash for this block than it was for the Genesis block, right? It's just a ratio. It's comparing the difficulty with this block against a reference point, which was the Genesis block, and that's basically because this shows you how much more hashing power, how many more hashes per second are available on the network now as compared to when the system first got up and running back in 2009. It's 258 billion times harder, and that's why it's essentially down to ASIC equipment and way beyond the realms of a kind of somebody running this software on their laptop to mine a block, right? Because it's so much more difficult now. And then the new value of the bits, again, as in the latest value of bits, is this. If we go back to our smart bit, we can see this is the latest block. We can see that the difficulty is 258 billion, and the bits is 1800044 right? 18044 So that is our entire fully expanded in hexadecimal. That's our entire target number. So any hash that is less than this number or equal to this number is a successful, was or would have been a successful candidate hash for this block. So guys, I hope that was useful. It's not the easiest subject. A lot of the documentation is a little bit confusing, and I think the message that above all that it's just about getting a certain number of leading zeros is, I understand it's a simplification that's made to make the explanation accessible to people without having to fully understand what a drawn out 256-bit number looks like, etc., etc. But it's really a misconception, and for those of you who are interested in sort of understanding what the difficulty is, what the bits is, what the target is, I hope this kind of cleared it up a little bit. If you've got any questions, please leave them down below. I'll get back to you, and really want to sort of clear this up for people. It's not the most important thing to understand if you want to understand the basic concepts behind Bitcoin and blockchain. But for those of you who are sort of digging around a little bit, thinking, well, what's this bits number, and how do I reach it, and how does it relate to difficulty, and what's the target, etc., then hopefully this has been a little bit useful there. So thank you very much for watching, and I will see you in the next video. Bye.